So, so where were we? So we had met the definition of divisibility, chapter 2. Starting nice and slowly, taking these things quite slowly. So this definition defined a relation amongst the integers. Okay, a relation meaning a binary relation, meaning it's a statement with two variables, basically. And we say A divides B if and only if there exists another integer C such that B is equal to C times A. Okay, so this applies for all pairs of integers A, B. A divides B if and only if there exists a complementary divisor, C. It may happen to be B itself, or indeed A itself. It may happen to be B itself, if A is 1, or it may happen to be A, B is equal to A squared. But there's some integer C that you can write B as a product of integers C times A. So equally well, you're seeing there that we would say that C divides A. Okay. You can call B a multiple of A and C and A divisors of B are factors. Okay, and there's a big warning on the page there underneath the definition, which basically warns you to get the notation the right way around, even if it's not big. There's potential for some confusion here about which number is doing the dividing and which number is being divided. So the one on the right is being divided by A, so to speak. The one on the left, A, is doing the dividing. Okay. Now, just doing a quick recap here. We had theorem 2.1. These were important basic properties of divisibility. In particular, one that seems to come up again and again, so it's just worth emphasizing it here to bring it to our minds. In particular, number 3, which is about the divisibility of linear combinations. So for every A and B, for every triple of integers, A, B, and C, if A divides B, and I may be using different letters here to what's written in the book, but no harm. No, I'm not. So if A divides B and A divides C, that implies that for every pair of coefficients M and N, you might care to name, A will divide M times B plus N times C. So the M times B plus N times C is a linear combination of B and C. And that property 3 is telling us that whenever you have A dividing the two integers B and C, A will automatically divide any linear combination of the two numbers from this. Okay, so A divides B and, that's the ampersand, and A divides C. That's going to imply that for every choice of coefficients M and N, for all M and N integers, A will divide MB plus NC. Then we met the fundamental theorem of arithmetic, just quickly reviewing things we've discussed already. The fundamental theorem of arithmetic basically says every positive integer n, can be written or factorized or expressed uniquely, that's important, as, and I'll write it like this because this is how we often see it. So n can be written as a product of powers of primes. So we're taking a product of the pi to the alpha I for I running from 1 to r. So this is where the pi are primes and the exponents alpha I are positive integers. So remember, just in case you're a bit rusty on it, that's the capital Pi, the product symbol, yeah? So just as a reminder, just as the sum of xi is x1 plus x2 plus x3 plus, or maybe it goes on for infinity, depending on the, say, I equals 1 to r. The product symbol, which is a capital pi instead of the capital sigma, capital pi xi, that would be x1 multiplied by x2 multiplied by x3 all the way up to x. Okay. Capital pi is the product operator symbol, and capital sigma the summations. Pi, of course, is the Greek version of p. Pi is a p sound in Greek, so it makes sense to use the pi symbol for product and the sigma symbol, which is equivalent of s, the symbol for sum. Okay. So although the product in the statement of fundamental theorem of arithmetic in the notes is written out in the usual multiplication notation, this is a compact way of writing the prime factorization of the integer. I've underlined the uniquely part there, so it's the uniquely part which we're not able to prove yet, okay? But we can we can do a proof at the moment, which I sketched out last time. We'll maybe write it out a bit more formally now. We can prove the existence part. The fact that every integer n can be written as a product of primes. The uniqueness part, the fact that it can be written essentially in one and only one way, that will have to come later. The uniqueness needs more theory. Meanwhile, it's pretty easy to appreciate that, say, a small composite number like 15 can be written as product of primes 3 times 5, and there is no other way to write 15 as a product of prime numbers. Prove that because there's only a handful of prime numbers less than 15. The only product of primes less than 15 that gives you 15 is 3 times 5. But for a number with a million digits, we've no kind of intuition, or we've no kind of reasonable way of proving directly, naively, that that has a unique prime factorization. Okay, we could have exhaustively checked, find all the primes that are less than it, and exhaustively check all prime products that are less than or equal to it, and observe there's only one that works, but it's not a very satisfactory way. So we will want a proof of uniqueness, okay? Build up enough theory about divisibility and how it works to be able to be completely certain that there aren't multiple ways of factoring, multiple different ways of factoring large integers. And it does have another reason why we should worry about proving uniqueness and care about proving uniqueness is there are other algebraic systems of number-like objects. Okay, not that are familiar integers or real numbers, but related algebraic structures of number-like objects where you've got operations of addition and multiplication, which are generalizations of addition and multiplication. Familiar numbers, and in some of those other systems, factorization into primes is not unique. There can be more than one essential way of decomposing numbers into products of what are in those systems prime numbers or irreducible numbers. So the uniqueness part certainly doesn't hold in all algebraic systems, so that's another compelling reason why we should worry about obtaining a proof of it and securing a proof of it for the integers. Okay? But for the existence part, we can prove it. Here. So we'll use strong induction. Strong induction on n. So we'll assume. Okay, we should have said, you can say up here every positive integer greater than or equal to 2. Okay, you can include 1 there as 1 is an empty product of primes. An empty product should have the value of 1. But anyway, so we'll assume the result is true for all n satisfying or for all k satisfying 2 less than or equal to k, strictly less than, or let's go less than n, say. No, we normally phrase it, phrase going from k to k plus 1. So sorry, I'll rephrase that as for every n between 2 and k. And now we'll prove it. Now we'll prove it for n plus 1. So, i.e., what we're assuming is that such n factor into the product of primes. So having made the induction assumption, you then want to prove it for the next case, to prove it for k plus 1. So we consider k plus 1. If k plus 1 happens to be prime, which it might be, well then there's nothing left to prove, because if you've got a prime number, how do you factorize a prime number as a product of primes? Well, it's just itself. Okay? It's just the product of one number, just itself. Okay? So there's nothing to be done. So if k plus 1 happens to be prime, there is nothing more to be proved. It does factorize into a product of prime numbers, namely just itself. Sorry, not that way. Thank you. K plus 1 happens to be prime. We have the prime factorization already. So otherwise, k plus 1 is composite. Hence can be written as k plus 1 equals r times s. Okay, it's a product of two integers where r and s are both between 2 and k. Because we're saying k plus 1 is composite. So if k plus 1 is composite, by definition it's not prime. So by definition it has a non-trivial factorization. Okay? A genuine way of factoring k plus 1 into a product of two smaller integers. So my bounds on r and s here rule out the case that you just trivially factorize this as 1 times k plus 1. Okay? So where r is 1 and s is k plus 1 or vice versa. If that's not a genuine factorization of a number, but if this number is composite, then it does have a genuine non-trivial factorization. Okay? But of course, when r and s lie in that range, we've made an assumption about, we've assumed that they can be factorized into a product of primes. Okay? R and s factor into products of primes by assumption. So then we simply, here's a nice technical word for you, concatenate the two factorizations. Concatenate, used a lot in computer science, is a word to say where you take two list-like structures or sequence-like structures and just join them together. Tag one onto the end of the other. Okay? So whatever prime factorization we have for R, and whatever prime factorization we have for S, we just concatenate them together, just list them together, and that would be a prime factorization for the number n. Okay? So concatenate these. To give a factorization of k plus 1. Okay, so therefore we proved the existence of these prime factorizations using induction. You should give a, we declared at the start we were going to use strong induction, so maybe we don't need to spell it out again. Okay? But you can see, like, so why isn't that a proof of the uniqueness part? Could we have just assumed that, you know, every n less than or equal to k had a unique prime factorization? And then the unique prime factorization from R and the unique prime factorization of S will glue together or concatenate together to give you unique prime factorization of K plus 1. But you can see that this argument on its own isn't enough to preserve uniqueness, because I made a choice here. We encountered a K plus 1 which was composite, not prime. But we have to make a choice to select one factorization of the K plus 1 as an R times S. But you're very familiar with the idea that composite numbers can have many different factorizations into products of smaller integers. 24 is 2 times 12, 3 times 4, that's it, 4 times 6. Yeah, so there's three different factorizations of 24 into smaller non-trivial factorizations. Okay, so who's to know that, if you're doing this induction part, that choosing those different factorizations into product of integers wouldn't lead to different prime factorizations for the number. Okay. So there's a kind of arbitrary choice involved at this point, which means that this kind of argument on its own doesn't establish the uniqueness of the prime factorization. Okay. Is that okay? Any questions about that argument? I mean, it's just a formal, fixed up version, a formal presentation of that thing we sketched out the last time using the factorization trees, where you keep factorizing the number as much as possible. Well, it's just a formal presentation of that idea using induction. Okay. So you can kind of regard the next theory that we're going to be working through, you can kind of think of it as a way of building up the necessary knowledge to be able to prove uniqueness of the prime factorizations. Okay? That's one way of thinking about the material we're going to see next. Okay, maybe I'll switch over. Yeah, there's some definitions coming, which we haven't seen before. So let's switch over to the notes to look at those, and then we've got a couple of results to argue for, which I'll switch back to the visualizer to talk through those. Okay. So we need to know, in order to prove uniqueness, we need to find out a bit more, build up a bit more theory about divisibility itself. Okay? So what we're going to do is look at how different integers, what kind of, how their divisibility properties can relate to one another. So we're going to look at the idea of common divisors. So the definition is fairly straightforward. It's a fairly good term. It more or less describes what it is. So an integer c is a common divisor of two other integers a and b, if and only if it's a divisor of both. Okay? Common divisor. C is a common divisor of a and b, if and only if c divides a and c divides b. So like 15 and 24 have a common divisor of 3, for instance. 3 divides 15, 3 divides 24. Any other common divisors of 15 and 24? 1. 1 is like a trivial common divisor of every pair of integers. Because remember that in that basic theorem about divisibility, we saw 1 divides everything. That exhausts any, okay, you could say -1 and -3 are also additional common divisors of 15 and 24. But we normally restrict our attention to positive numbers when we're discussing divisibility, because whatever divisibility is displayed by positive numbers is kind of automatically reflected on the other side by the appropriate statements involving their negative counterparts. So you don't gain anything by searching for negative divisors. Okay? Saying that 1 and 3 are the only common divisors of 15 and 24 is the full story about 15 and 24. Okay? It's automatically true, -1 and -3 are also common divisors, but it's not worth mentioning. So definition 2.4, and this is indeed something you may have seen before as well. Well, if any pair of integers a and b have common divisors, there'll be a special common divisor, which we're picking out as the greatest common divisor. Okay. The least common divisor of a pair of numbers isn't that special because it's always going to be 1, because 1 divides everything. But the greatest common divisor of a pair of integers will, in a sense, tell us what commonality or what kind of overlap there is in terms of divisibility between the two integers. We use the good suggestive notation GCD, A and B, for the greatest common divisor of two numbers A and B. Just a bit of a warning, you will see in other books, other authors, they use the very minimalist notation of just simply brackets AB to denote the greatest common divisor. Okay, it saves a bit of space writing GCD all the time, but I much prefer actually writing GCD because it tells you what it is. It's a good reminder. But just be aware, if you do pick up other number theory texts and you just see them talking about this bracket AB all the time, it could well be that that's the notation they're using for greatest common divisor. So just check where they define greatest common divisor in the book and where they set up the notation for it. So again, with small numbers, you can kind of run through all the possible combinations in your head and quickly alight on the greatest common divisor. Okay, the greatest common divisor between that example 15 and 24 is 3. There is no larger number that divides 15 and 24. A couple of other examples here. GCD of 2 and 4 is 2. GCD of 30 and 42 is 6. But then, if we see options like this, GCD of this large number and this other large number, it's just randomly bashing the keyboard there to type those in. But I mean, what's the greatest common divisor of those two? Okay, I don't expect an answer. But, or even how would we go about finding their greatest common divisor? That's not so clear to us, okay? Although you may be aware of it. Okay, so this question has a very nice answer. There's a very good algorithm for finding greatest common divisors called the Euclidean algorithm, which is a basic algorithm, doesn't use anything complicated, just simple integer arithmetic operations, and it can very quickly find the greatest common divisor of pairs of numbers. And when I say very quickly, of course, any computing task based on numbers is probably going to depend somewhat on the size of the inputs you give it. But even if you give gigantic numbers to the Euclidean algorithm, as long as they're numbers that will fit into the computer's memory, as long as the computer can work with them, it will more or less instantaneously be able to tell you what the greatest common divisor of those two numbers is. So it's an extremely fast algorithm as kind of computational number theory algorithms go. So it's an extremely good algorithm. As opposed to algorithms for finding complete prime factorizations of arbitrary large integers, those, although you can describe such simple algorithms, but they don't work as fast as, say, something like the Euclidean algorithms that we're going to see. They still aren't that fast. So when you give it a large integer to find the prime factorization of, it doesn't. The length of time the algorithm needs to run depends strongly on the size of the integer. But we'll discuss that in more detail, and John will be discussing that in more detail as well. Okay, just another couple of bits of terminology. We have this notion of coprime or relatively prime. So we say a pair of integers are coprime to one another when their greatest common divisor is 1. So that means they don't share any common divisors at all, apart from the trivial one of 1, which automatically divides everything. So every pair is definitely going to have a common divisor of 1. But if there is nothing else, no other positive common divisor, then we say the pair of numbers are coprime, or relatively prime to one another. Okay, and this is an important concept as well, because it's saying if A and B are coprime, it's saying kind of that they're completely unrelated in terms, that they're as unrelated as they can be in terms of their divisibility properties. Okay? Apart from 1, which boringly divides everything, apart from that, there is no other number that divides So that's kind of special behavior. It's saying that A and B, are completely different in terms of their divisibility. A quick example there, example 2.3, 10 and 21. Okay. There's no number, no positive number apart from 1 that divides into 10 and 21. Okay. So we're basically still stuck with this question here. How to find the GCD of arbitrary pairs of numbers. Okay. Is there a nice simple method by which we can do that? And there is. There's an algorithm to do it, called the Euclidean algorithm. And the algorithm uses, I'm just going to switch to the overhead now, so I'm just going to simplify the presentation a bit. So the Euclidean algorithm, which will be for finding the greatest common divisor of a pair of integers, is based on the operation, and this is what's defined in theorem 2.2, and it's called integer division with remainder. Again, it's not the operation itself is not deep or complicated. You're extremely familiar with the idea already, and indeed, it's something you learned in primary school. I can remember chanting these kind of things in primary school. You'd be going through all the numbers and you'd be chanting out 10 is equal to 3 times 3 with the remainder 1. 15 divided by 7 goes 2 times with remainder 1. Okay. So taking an integer, attempting to divide it by something, if it does divide cleanly, if it's divisible by it, in our terms, all well and good. But even if the number is not completely divisible by something else, you can still do your best job at writing it as a multiple of it, and then there'll be a small little remainder left over. Okay. 24 is 1 times 15 with the remainder of 9. So integer division with remainder. Okay. So given any A and B, any pair of integers A and B, as long as the B is non-zero, we can write A some multiple Q times B plus a remainder R. And we can do this in an essentially unique way, no, in an exactly unique way. So this is A is some number of times B plus a remainder R. And this remainder has this nice property that it is greater than or equal to 0, so it's non-negative, and it is strictly less than the absolute value of B. So it's a small remainder. The small remainder left after you divide A by B. So if you divide 10 by 3, you can write 10 is 3 times 3, so Q is 3 there as well. 10 is 3 times 3 plus a remainder of 1. You wouldn't write 10 is 2 times 3, 6, with the remainder of 4. It's still true, 10 is equal to 2 times 6 with the remainder of 4, but that's kind of, you wouldn't necessarily describe 4 as the remainder left after division because you can divide it again by 3. You can take a further 3 out of the 4 and leave a smaller number, which is more properly called the remainder. Okay? And the Q and R are unique for a given A and B. Okay? So there's one and only one way to do an integer division with remainder. So why is that presented as a theorem with a proof rather than, say, rather than presented with as just a definition, well, again, there are a couple of claims there. Okay, we can write A is Q times B plus R. That maybe for, in general, maybe you should have to justify that, and that this can always be done uniquely. Okay, so these two things are addressed. Proof of these claims is in theorem 2.2. Okay, but I won't talk through the technicalities of the proof here. Rather, I'd like to explore the following proof. First of all, we'll just do a couple of quick examples. So the following proof, because it's a much more interesting result related to the greatest common divisors. So just as in case there's any doubt, so if A is 10 and B is 3, you can write 10 equals 3 times 3 plus remainder 1. That's integer division with remainder. If A is 27, B is 4, then your 27 is what? 6 times 4, 24 plus remainder of 3. Okay. So in each case, you see the R, the remainder, is smaller than B. 3, the remainder, is smaller than the 4 that we divided it by. It looks slightly quirky if one of the numbers is negative. So for instance, okay, let's say the A was 27 and the B was minus 4. Okay, how would we do integer division with remainder there? Well, we'd want to do a multiple of B. That leaves us, you see, that the request is that the remainder is always non-negative. So we'd have to take a multiple of minus 4. That would take us to the other side of no, I'm thinking what A is. Okay, so this would still be, sorry, this would just be minus 6 times 4, which would still give you 24. Sorry, plus 3. Sorry, something I'm thinking about is if let's say A was, what am I thinking of? What am I trying to do? If A was minus 27 and the B was 4. That's the only way in which it might look slightly quirky. Then the minus 27, this time we take a multiple of 4. That would bring us to the other side of 27. So we go minus 7 times 4 to give us minus 28, and then that will allow us to add on remainder 1 to get to minus 27. Okay. But most of the times we won't be meeting, you won't actually be using it in negative arguments. When we're using it in practice to carry out the Euclidean algorithm, the inputs will be positive. So this operation, performing a division of A, of an integer A by another non-zero integer B, and finding the quotient Q, so you can call Q the quotient here, and R the remainder. This is called integer division with remainder, and the Euclidean algorithm is basically based on repeatedly applying that in the appropriate way. And that's what I'll probably discuss with you. Well, we will certainly discuss it tomorrow. But for the moment, the next task to do is to prove something about the greatest common divisor, which is very interesting. And I think is the first, maybe the first non-trivial result we've seen, or the first proof of something which isn't kind of obvious, or which I don't think when you're coming to it for the first time, I don't think you have an intuition about it that would tell you that this result kind of must be true. And this is theorem 2.3. And this is a description of, or it's a property of, the greatest common divisor. Or as it's termed here, a characterization. characterization of the GCD. A particular and a very appropriate and a very useful way to describe the GCD of a given pair of numbers. Okay? So what do we have here? What's the statement? So we've got let A and B be integers, not both 0. Okay, yeah. Yeah, I mean, if you ask yourself what's the greatest common divisor of 0 and 0, you get kind of stuck in a bit of a loop. Because remember, from our basic properties, everything divides 0. So in some sense, then, there is no greatest common divisor because whatever number you care to name is a common divisor of 0 and 0, because everything divides 0. But then in another sense, but you can kind of fix it by definition, you can define the greatest common divisor of 0 and 0 as 0, because kind of 0 is the biggest number in the divisibility sense, because everything divides it. Right, yeah, so there's a bit of a mind warp about asking what GCD of 0 and 0 should be. And so anyway, we remove that complication. So we're not talking about 0 and 0, because that's a kind of awkward or side case. So if D then is the greatest common divisor of A and B, whatever that might be, then, and this is the result, there exists a pair of integers, M and N, such that, and this is the kind of magical thing, this greatest common divisor is equal to MA plus NB. In other words, it's a linear combination of A and B. In particular, D will be the least positive linear combination. Okay, the smallest positive number that you can achieve as a linear combination of A and B. And there's a moreover added to it, but that it's really a corollary to it. If we know that the greatest common divisor of A and B can be written like this as a linear combination, then thinking back to our properties of divisibility, any common divisor of A and B will automatically divide this linear combination, okay? Because that was the divisibility of linear combinations result. So any old common divisor of A and B will divide D, will divide the greatest common divisor. So the greatest common divisor is kind of special or prominent because not only is it the largest positive number which divides into A and B, but everything else that does divide into A and B, it is a common divisor of A and B, divides into the greatest common divisor. Okay? So the greatest common divisor kind of embodies all of the common divisors. And that comes from this result. Okay? But it's, as I say, it's, I think, the first result we're meeting, which is maybe a little bit of a surprise or unexpected when you first see it. Okay? So why is it that the greatest common divisor of two integers happens to be a linear combination of the two, and a special linear combination, the smallest positive? Okay. Okay, so the proof works using induction in a sense, but it uses the well-orderedness principle, which, remember, in the first chapter we said was something that was equivalent to induction. The well-orderedness says that every set of positive integers has a least element. Okay? So the set we consider S, which is the set of all linear combinations. Set of all linear combinations of A and B. So it's the set of everything you can write as an alpha A plus a beta B The only restriction is that alpha and beta, the coefficients, are integers. It's kind of a nice way of proving this. We're tasked with proving that the greatest common divisor is a certain special linear combination of A and B. So we immediately form in our minds or consider the set S, which consists of all linear combinations. Okay, so this is certainly an infinite set. When you think about it, certainly the set S does contain positive and negative numbers. Okay, granted, we don't know whether A and B, if A is positive or negative, or B is positive or negative. It could be positive or negative, A and B. But the alpha and the beta are allowed to be positive and negative. So certainly this set S, if you choose the signs appropriately, you will be able to generate positive numbers as linear combinations of A and B, even if they're both negative. So that means it is something we can apply the well-orderedness principle to. So let D be the least positive element of S. Okay, the smallest positive number that is in S. Okay, such a D exists. Okay, I'm varying the wording slightly from that in the book. Such a D exists by the well-ordered principle. Well-orderedness of Z. Just trying to get the main ideas down from the notes and just discuss it in a nice way. So the claim is that this D is the GCD of A and B. Okay, that's the claim that we're about to prove. And here the proof is it's really like a proof by contradiction, if you like. So D is written as MA plus NB for some M and N. Okay, that's true because it comes from S. D is an element of S. S is the set of all linear combinations. So D is certainly a linear combination. So we're trying to prove that D is the greatest common divisor of A and B. Well, we're going to suppose that D does not divide A. Suppose D does not divide A. Well, if that's the case, then we can perform integer division with remainder. This process which we just described, we can perform integer division with remainder of A by D. So A will be Q times D plus some remainder R. Now, the integer division process with remainder says that the remainder R is bigger than or equal to 0 and strictly less than D. But we're assuming here, see, we've supposed here that D does not divide A. So that means the remainder R must be strictly bigger than 0. Strictly bigger than 0 and strictly less than D. Well, if we focus this equation now on R, we'll have R is A minus QD. But D is already a linear combination of A and B. So by reorganizing that equation, we see again that R itself is a linear combination of A and B. Okay? R can be expressed as a combination of A and B with integer coefficients, 1 minus Qm on the A and minus Qn on the B. Okay? So this implies that R is an element of S, the set of all linear combinations. And we have this condition here, which I'll just repeat down here. R is strictly less than D. And that's when the red lights go off. The alarm goes, you've proved a contradiction. And either this means everything in the world is chaos, and everything is true and everything is false, there's no meaning to anything. You get a slight flutter of the heart and you think that for an instant. Or you think, oh no, it's okay, I haven't caused a contradiction, the contradiction came from a mistake. You see, D was the least positive element of S. And here we seem to have found a smaller positive element of S. That's the contradiction. How could something be smaller than the smallest thing? It's a contradiction. Nonsense, okay? If that were true, the universe dissolves. But it's not true because it came from a mistake. The mistake we made was this: suppose D does not divide A. That's what allowed us to form this contradictory R. Okay? So D does divide A. Okay? It can't not divide A because that leads to a contradiction. So D does divide A. Similarly, D does divide B. You can run exactly that same argument, little proof by contradiction, that if we suppose that D did not divide B, then we would get another contradiction. So D is a common divisor of A and B. Okay, this number, the smallest positive linear combination of A and B, the special D, smallest positive linear combination of A and B, it is a common divisor. And by theorem 2.1 part 3, which is what I reminded you at the start, which is the divisibility of linear combinations, every other common divisor of A and B divides D. So D is the greatest common divisor. So it's a really nice proof that. Good use of proof by contradiction in the middle of it. Good use of the well-orderedness principle to prove that such, just to be sure that such a thing exists, the smallest positive linear combination of A and B. But then this unexpected result that this D, which is the smallest positive linear combination of A and B, it is actually the greatest common divisor of A. That's an extremely useful result for us, and it will tie together a lot of things, and it will ultimately allow us to prove the uniqueness part of the fundamental theorem of arithmetic. Okay? Which is coming in chapter 3. So when I see you tomorrow, we will meet the Euclidean algorithm, and that will more or less finish off chapter 2 for us, for the exercises. Okay? So we'll meet Euclidean algorithm tomorrow, and it'll feel like a more practical hands-on session with the Euclidean algorithm.